Good evening, friends. Today's lecture is about this technique and meteorological parameters derivation using GPS GNSS. Now, this whole topic can be put under the category of GPS meteorology, where we are using GPS GNSS constellation for the deriving various meteorological applications. Now, when I say radio occultation, before that, I would like you to understand what do we mean by occultation. So let me go to the next slide and make you aware of what occultation is. So the earliest known account of occultation was the astronomical and the planetary occultation. Now, as you see, the right figure is actually showing a moon surface, and it is gradually progressing, and the object in the background is the planet Saturn. So what happens after a certain time, this moon will actually progress and obstruct the Saturn, so it will not be visible. Now this was the earliest known example of the occultation, and on the left you see an animation where an asteroid is progressing and then a distant star at the background is getting obstructed by the asteroid. So this is another example of the occultation, which can be called as asteroidal occultation of distant stars. Now, in both these occultation phenomenon, which were natural, occultation you would actually mean is the physical disappearance of the object in the background by an object in the foreground, and because it is in the foreground, they appear to be apparently larger. So that will move and it will obstruct the object in the background. So it is immaterial whether the object in the foreground is moving or the object in the background is moving. What matters is the relative motion between the two. So this was an inspiration which was very much widely used by astronomers to derive certain parameters for the planetary studies, like the dimension of the planets, the brightness of the stars. So all these were the earliest known applications of this occultation phenomena. So let's see what are the various commonalities of this astronomical or planetary occultation. So in all those phenomena, the important 4 points are that they have been happening on the polychromatic signals, which means the occultation signal actually spread across the electromagnetic spectrum. Now, if I can quote an example from total solar eclipse, if you recall, the sun's spectrum is across the whole electromagnetic band of the frequencies. So it means you are not just using one particular frequency, whereas you can get information from all the various frequencies depending on what type of applications you want to do. So they fall under the polychromatic signals. Second, that these are non-maneuverable natural phenomena. Now you cannot control the motion of astronomical or the planetary bodies. So that makes it difficult to tune it for your particular applications. You have to be guided by their own motions. So they are self-sustaining natural phenomena. As a corollary to the second point, that would mean that these events will also happen at their own frequencies and time. So they are far and few in between. For example, you don't get solar eclipse every month or every few months. So it may have a span of around a year or 2 years or 5 years, depending on what is the trajectory and the orbital motion. Okay. Fourth point is about the measurables. So what earliest astronomers were deriving were mostly the structure and the dimensions of the astronomical bodies. So if you today talk about radio occultation, how does radio occultation is different from these astronomical and the planetary occultation? So we will see it in the next slide. Now, radio occultation stands for occultation of radio signal transmitters by the intervening astronomical bodies having essentially an atmosphere with the signal received through refractive bending. Now, what we are seeing different is, instead of polychromatic signals, which were the forte of the astronomical occultations, Here, the signals are confined to radio frequencies only. So that is one change. Second, that you are making use of radio occultation to know about the planetary atmosphere. Particularly, we are applying it for the Earth's atmosphere here. And you have an independence of maneuvering the orbits, which was not possible in the natural occultation phenomenon. Here, we can design the trajectory and to suit our particular applications. Third point, that we can also devise customized receivers, and these receivers are actually custom made to get the signals safe from GPS and other kind of the global navigation satellite systems. Fourth point that is also important and not and to be kept in mind is an understanding of the physics of the signal atmosphere interactions. So we will see it one by one. Now let me first of all, to enlighten you, show you this schematic diagram of radio occultation technique. Basically it falls under the limb sounding technique. Now what is limb sounding? When you see this is the planet Earth and it is surrounded by various concentric layers, which are the different layers of the atmosphere. So atmosphere has been divided, just for the sake of presentation, into different concentric circles. And you see on this side, this is the GNSS transmitter. On the other side, you see the receiver, which is moving, and at different time, it is at different points. Okay. Now let us see the first case. Here, the GNSS transmitter transmits, and the ray follows this trajectory and is being received by the low Earth orbit receiver on the other side of the planet. Now, when you sound the planetary atmosphere from one side of the planet to another side of the planet in a limb kind of fashion, this kind of sounding is called the limb sounding technique. The other contrary to this is the nadir sounding, where what happens, you are actually, satellite is somewhere here and you are sounding directly towards the downward direction. So that example is the complementary to the limb sounding technique. So you must remember that radio occultation is a limb sounding technique. Now what happens? Let's say at time t equal to 0, this signal is propagating and is being received by the receiver across the limb, and the signal is just scanning the ionospheric layer. So in the ionosphere, the parameter that you can derive is the refractive index, and then you can derive from the refractive index the electron density as a function of height. The h shows you the height. So it means with each successive times, the signal is actually scanning one by one these different layers of the ionosphere. So as the signal is moving from one, say, top of the ionosphere to the bottom of the ionosphere, you are actually scanning different layers of the ionosphere, and for each height h, you get an electron density profile, which we actually derive from the measurement of the refractive index of the ionosphere. Now, as at the outset, I would like to say that we will here divide the atmosphere into two broad layers. First will be ionospheric layer, and below ionosphere, I'd say start from 60 kilometer to the surface of the Earth. Then that particular layer or the combination of atmospheric layers will be called as the neutral atmosphere. So just keep this in mind. We will be seeing the parameter derivation for the neutral atmosphere separately. Now in the neutral atmosphere, there are basically three different atmospheric layers: the mesosphere, the stratosphere, and the troposphere. Now as you see at different times, let's say the second signal, by certain amount of time, after a certain amount of time, this signal is now passing through a different layer of the atmosphere, and it has entered into the neutral atmosphere. So what happens here, you no longer are measuring the refractive index of the ionosphere and the electron density. What you are actually measuring is the refractive index of the neutral atmosphere, and from this you are deriving the temperature and the water vapor pressure profile Again, it means as a function of height, right from 60 kilometer down to the surface of the earth. So these are the important measurables that we are going to see how to derive these parameters. Now let us say what would be the strength of this radio occultation technique. So in the box you see the 7 points. These are the chief characteristics of radio occultation technique. First is that it is a very high accuracy technique. Here it is possible to obtain the profiles to as good as 0.1 K in the certain regions of the atmosphere. Second, we get assured long-term stability. Now, by long-term stability, we means that these data will be very much good for the applications in the climate research initiatives. So, why this is happening? Because here, what happens is the signal which is transmitted by the GPS at a particular time is being received by the LEO at a particular, at a later time. What the signal is measuring, what the receiver is measuring is just the time tag of the signal. Now, because of the availability of very stable and precise atomic clocks on both the receiver as well as the transmitter, which are highly accurate and calibrated, these clocks drift over a very long period of time, say millions of years. So because of this high precision of the clock, basically the basic raw measurement of the GPS in the GPS radio occultation technique is a stable measurement, and that ensures that we are able to get the climate quality data. Third, that it is an all-weather technique which can be applied even during the rainy seasons, during the high rain rate situations, or maybe when the clouds are present, or when the ice clouds or maybe water clouds are there, which actually cause problems for the nadir-based sounding, which are based on the IR infrared frequencies. Fourth, that it is able to provide you with a global 3D coverage. And as I said, basically in the radio occultation, you are able to define the trajectory. Now, choosing a trajectory will help you to define the coverage of this limb sounding technique. Fifth, which is a very important point, is that it is able to provide you a very high vertical resolution data. And in the lower troposphere, you are able to get it at around 100 meters. And with a higher altitude, the maximum that it can be reached is about 1 kilometer in the stratosphere. So that too is not provided by any other technique. So that is why it has an upper hand in terms of when you compare it with other sounding technique. Sixth, it is able to provide you independent height and pressure data, which is basically a kind of an innovation in this technique and not present even in any other satellite sounding technique. Seventh, from the economic point of view, you will find that this sensor is very compact, it is low power, and you have to devote just a small amount of money to put it in the orbit. Why this is possible? Because you see, you are not actually designing the transmitter. Transmitter is already there in orbit in the form of GPS and the constellation of it. And then you can also add on with other GNSS constellation. Let's say the present day, you can talk about GLONASS, you can talk about Galileo, you can talk about the Chinese constellation satellite system. Then you can also talk about the Indian regional navigation satellite system. So any of these combination can become your transmitter, and then you only have to design a receiver and put it in the low Earth orbit. So let us see the next, what is the GPS constellation, and understand some signal elements aspect. So this is a schematic of the GPS constellation. Basically, GPS is a constellation of today 32 satellites, but you only require 24 nominally, and the rest of it are in the form of redundancy. Whenever some satellites are down, then the other satellites replaces those. Second, these are distributed in the 6 circular orbits with a 55-degree inclination, and the orbital period of GPS is 11 hours 58 minutes. Now, when we talk about the GPS signal characteristics, basically it has 3 different parts. First, it is the it consists of a carrier signal, and these are at two different frequencies, L1, which is 1.575 gigahertz, and L2, which is at 1.22 gigahertz. Second, it is encoded with a navigation message, and the third, it is also modulated by certain pseudo-random codes, which are also called the spreading sequences. Now these are two, the codes acquisition code and the precision code, P of Y code. We will just see in the next slide the mathematical representation of the GPS signals. Now, the first equation, it is S at L1. So this is the signal mathematical representation for the L1 band GPS signal. It consists of two terms, as you see. The second signal is for L2, and it again consists of only one term. Now, the X is the C by A code, and P of T is the precision code. D is the navigation message, which you just seen. It has to be modulated on the carrier frequencies. The sinusoidal and the cosine functions, these are the two, the carrier frequencies. One is the in phase, the other is the quadrature component. So this is the final representation of the GPS signal, which is transmitted by the GPS satellite. Now, this is a particular electronic representation, how you are generating the signal. So as you see, the sinusoidal function for L1 as well as L2 are these high frequency signals at these frequencies, and the clear acquisition code is represented by this. It is repeated at 1.023 megahertz, whereas the P code is a longer code than the C by A code, and it is therefore generated at 10 times the frequency for the C by A code. The message, the navigation message, is generated at 50 hertz, and these messages are important because they carry not only the orbital information of each of the 32 GPS satellites in the constellation, but also the information with respect to its health of the satellite, then various other information about which are important for the GPS satellites. All these are present in the navigation systems and the message, which are modulated in this fashion, and then the final L1 and the L2 signals are generated. Now, after this, let us now understand the physics of this GPS signal propagation through the Earth's atmosphere. So first thing we will see is how ionosphere is affecting the GPS signal propagation. Now, as we know, ionosphere is nothing but it's a whole layer consisting of ionized particles, okay? And because of the presence of the ionized charged particles, the dispersive effect is dominant in the ionosphere. So L1 and L2 signal with their different frequencies will actually be dispersed when they enter the ionosphere. And as you see in the right side figure, they are actually traversing two different paths just after the ionospheric layer. And they continue to follow their different paths till they are received at the receiver on the other end of the limb. So this happens because of the dispersion effect in the ionosphere. Now, the presence of electron in the path of the signal actually causes the signal to be delayed when they are received at the receiver. By ionospheric delay, I mean that if the ionosphere was not there, then the travel time of the signal would be something which is independent of ionosphere. Now suppose it is some time t. Now if you add ionosphere, and let's say the time which the signal takes from GPS to LEO in the presence of ionosphere is say t2, then the difference t minus t2 is the delay due to the ionosphere. So this is the simple concept of what is ionospheric delay. So this delay is important, from which we will see how we are deriving the electron density concentration. Now this delay, as you know, it is dependent on the frequency. That is why you see L1 and L2 are basically delayed by different amounts in the ionosphere. Now L2 has a lower frequency, so what you would expect is that it will be delayed by a larger amount than L1. Now it is very interesting that for navigation, these ionospheric delays becomes a noise kind of thing. Whereas in radio occultation, these delays become important and advantageous because they can be used to correct for the ionosphere when we are deriving the parameter in the neutral atmosphere. Now, second effect which is actually present in ionosphere and actually manifests itself in the form of tracking loss of the signal is the scintillation effect. Now, this scintillation effect is happening because of the irregularities in the ionosphere, and these small scale irregularities are basically changing the amplitude and the phase of the signal in a very rapid and random manner, which is called as the scintillation. So we will see that sometimes this scintillation affects the tracking of the signal and sometimes we lose track of the signal. Now, what about the neutral atmosphere? Now, neutral atmospheric medium, as I have already said, actually is characterizing the layer of the atmosphere right from the 60 km to the surface of the Earth. The first effect that we will see is the atmospheric delay. Similar to ionospheric delay, here why the signals are delayed in the neutral atmosphere we will see. Normally we know that in the atmosphere the density profile is not uniform, and this actually what it means is that because of the non-uniform density profile, your refractive index gradient is non-zero. Because of this, you will see that the ray which is traveling from the GPS to the receiver will actually go through the refractive bending. This refractive bending is what is summarizing the essence of the radio occultation technique. So basically now atmospheric delay is manifested in terms of geometric delay and the retardation effect. Let me little bit throw light on both of them. Now, as you know, in the presence of vacuum, what happens is the signal actually travels through the straight line, which is the rectilinear propagation of the light ray. Now, and Fermat's principle tell you, you are aware of Fermat's principle in optics. Fermat's principle tell you that between 2 points, light always follow the path which takes the optimal amount of time. Now, when there is a presence of atmosphere, the light will actually choose the path where it is taking the shortest time. Naturally, when the atmosphere is there, the signal will bend so that it corresponds to the time which is the shortest. Now, this particular bending from the straight line scenario is what is called the geometric delay. And the other effect, which is the retardation effect, is because of the presence of refractive index, what is happening is that your refractive index is defined as the ratio of the speed of light in vacuum to the speed of light in the medium. So when the signal encounters atmosphere, it slows down. This slowing down also causes the delay in the arrival of the signal at the receiver. So this kind of effect is retardation effect. Combinedly, what you see is the total tropospheric delay, which is now can be written as I have written in retardation effect plus geometric delay. Mathematically, delta L, which is your delay term, the total combined tropospheric delay, is the integral of refractive index as a function of the S is your signal path minus 1 ds plus S minus G, where S is your actual curved path length and G characterizes the straight line path. So this is your geometric delay, and this part when you separate out is your retardation effect. So we will see this delay is the most important thing which we are utilizing to derive the parameters like temperature and water vapor in the neutral atmosphere. What are the other effects? Let us see in the next slide. Second effect that I will talk about is the attenuation of the GPS signal. Now GPS signal, as I said, L1 and L2, they both come under this band 1 to 2 gigahertz. At this 1 to 2 gigahertz band, oxygen attenuation is dominant, okay? And this attenuation is anisotropic. So when it is anisotropic, it means that depending on what is the angle, the elevation angle of the GPS satellite, the attenuation will be changing from one angle to the other angle, and therefore it is not isotropic. The other gas which is present in the atmosphere is the nitrogen, which is the most abundant gas. Now nitrogen attenuation is negligible at the GPS frequencies, so we need not worry about the nitrogen attenuation. Now we see what about the rainfall attenuation. So as I said, we were talking about all weather capability of the GPS technique. So if there is no appreciable attenuation in terms of say rainfall, then we can say that this technique can work in the all weather kind of situations. So let us see how rainfall affects the attenuation. Now I will show you through this illustrative graph. Now it is taken from, adapted from a very important book. You may refer it. It is a book on Ulabi by Ulabi on microwave remote sensing. And these two plots have been taken from this reference. Now what I am showing is on the x-axis is the set of frequencies. Our GPS frequencies are here, 1 to 2 gigahertz. And on the y-axis I am showing you the specific attenuation in terms of the decibel per kilometer. This is the loss, logarithmic loss per kilometer. And you see the different graphs are shown for the different rainfall rates. So the highest rainfall rate which has been considered is the 150 millimeter per hour, and it is shown by this curve. Now you see for the highest rain rate that you can get on the earth, our GPS signal attenuation is just even less than 0.01. So definitely for even dense rain rate, you don't get the signal to be attenuated because of rainfall. And naturally the lower rainfall rate will be subsequently having negligible attenuation on the signal of the GPS. So definitely we have seen that rainfall will not be affecting our signal. What about the other thing? Let us say about the effect of clouds. And in clouds, we can talk about the water clouds as well as the ice clouds. I am showing this effect in the right plot. Now you see what I am showing is on the x-axis is the frequency, this one, and the GPS frequency is on this side. So 1 to 2 gigahertz, and it is increasing as we go from the right to left. And on the y-axis I am showing, instead of attenuation, what I am showing is percent transmission. So how much is the signal allowed to be transmitted and not attenuated. So I'm showing about the transmission. Now you see at GPS frequencies on this side, this is 100%. So whatever signal is passing through clouds, it is 100% transmitted to the receiver, whether it is ice cloud or whether it is the water vapor clouds. So again, it makes sure that this technique is able to give you signal and measurables even when there is presence of rain, extreme rain events, or in the presence of the clouds or the ice clouds. Okay, so next effect that we will see is the scintillation effect. Now we know, as we have seen, that scintillation also affects the signal in the ionosphere. There what it does is it actually manifests in terms of the tracking loss. And here we will see that again in the lower troposphere, because of the rapid changes in the water vapor domination, and the concentration of water vapor changes both temporally, very fast, and spatially also. These scintillation effects manifest in terms of rapid fluctuations in the amplitude and the phase of the GPS signal, and it also results sometimes when it is very large in the loss of signal, and therefore it does affect our GPS signal. So we have to take care of the scintillation effects when we are actually trying to process the GPS signals. So after considering about the physics of the signal atmosphere interaction, let us see what is the other component. We have talked about transmitter, we have talked about the signal interaction and the physics, and now we will consider about the receivers. Now basically a GPS radio occultation receiver will consist of these three components. First is POD antenna. POD stands for Precise Orbit Determination Antenna. Now this antenna is actually used to get the navigational information of the satellites. So we will see in the later part of my talk that how we also require information with respect to what is the orbit, what is the time, and what is the actually the orientation of the orbit, and these informations are important while we are processing the GPS data. So POD antenna takes care of this kind of information. Occultation antenna takes care of the occultation signals which are received at the receiver, and I have said to you that what is the basic measurable is the time, the phase, and the amplitude. So these are recorded by the occultation antenna. And the third part of it is the receiver unit. The receiver unit actually is the onboard consists of the various onboard softwares and the algorithms which actually processes and then actually gives us the various the process signals back to the ground for further post processing. So the observables in radio occultation limb sounding are signal phase delay and the signal amplitude, or we can also refer technically as the signal to noise ratio. Now, I said that radio occultation technique is maneuverable, whereas your planetary technique was not maneuverable. Now, how we make use of this maneuverability? You see, we can define the trajectory of the sounding technique by considering that which is suiting our particular region. So let's say I'm quoting from two real radio occultation missions. One is our own ISRO's Megatropic ROSA mission, and the other is the COSMIC mission. I'm showing the plot for ROSA mission on the left hand side, and on the right hand side is the plot for the COSMIC mission. Now you see, in ROSA on Megatropic mission, our objective was to actually trying to get the tropical data, and therefore we designed the trajectory so that the inclination of the orbit is kept at 20 degree. Because of this low inclination orbit of the satellite, what you are seeing is that mostly the data is confined within 35 degree to south and north of the latitude. Whereas in COSMIC, the objective was to have a global coverage. So there, by tuning the orbit inclination to 72 degree, what was achieved, that you can see you are getting the cosmic radio occultation data right from say 80 degree north to 80 degree north to 80 degree south. Okay, so this actually tries to enlighten you that you can actually now play with this technique when you are trying to cover a particular region. You are designing the orbit in such a way that your radio occultation data is coming for that particular region. And what happens is that in this technique, most of the time, as I said, there are certain issues which have to be taken care of, and we have seen the tracking loss because of scintillation effect in the lower troposphere. So these signals many a times are not able to penetrate right up to the surface of the Earth. Theoretically, you can say that the technique allows you to get the signal and the data right up to the surface. But because of the operational constraints and various errors and noises present in the data and the tracking losses, your signals are often restricted to around 0.5 kilometer to as high as it can go up to 3.5 to 5 kilometers. So that is one of the constraint, and it is also one of the research areas where people are trying to come up with advanced tracking algorithms so that we can further improve upon the signal to noise tracking losses and get the data right up to the surface. So in this plot, which I have generated from the cosmic data and processed for the global coverage, you can see that the purple colors are around 0.5 to 1 kilometers. So most of the time you are getting data right up to 0.5 to 1 kilometer. But as I said, in the tropics, the concentration of the water vapor is very large, and the fluctuations in the signal is also happening more in the tropics. So you see most of these dark blue patches and this green are showing the higher value of the penetration depth, where the value is ranging from around 1.5 to 2.5 kilometers. So this is the lowest height where you are getting, up to which you are getting the radio occultation data. And there are some red patches also you are seeing, but these are limited by the topography of that region. Actually, this is corresponding to the Himalayan region, where itself the height of the topography is around more than, on an average it can be around 5 to 6 kilometer, but it can go even up to higher at certain mountain peaks. Okay, so that is also limiting the lowest penetration depth. Okay, now let us now go to understand the technique's geometry in some more mathematical details. What I am showing in this slide is the occultation plane cross section. Okay, here I am showing the GNSS transmitter. The dashed line in this direction is showing the velocity of the GNSS in this direction, and the UG refers to the negative direction of the propagation of the signal. The ray path is shown by this line, and you see there is starting to bend, and then again it comes and is received at the low Earth orbit receiver. The low Earth orbit receiver is moving with the velocity VL in this direction, and the signal direction at the reception point is denoted by UL. So when you see this signal starts to bend somewhere here, the point somewhere here which is closest to the surface of the earth is called the tangent point. Okay, it is sometimes also called as the ray perigee point. Now suppose that just at the time when it starts to bend, the signal, if it had not bent, would have gone and followed this direction. Okay, you all agree? Then what happens? Suppose if this is the direction in which the signal is received, and you trace this direction back in a straight line path, then it would have intersected this line at this point, just making this angle. This angle is called the bending angle of this particular bending of the ray path. Now alpha is your bending angle, and another important point of which alpha is a function is the impact parameter. Now let me just clarify what do we mean by impact parameter. This PG and PL, which is connecting the center of the earth to the point where the bending has just stopped and where the bending has just started, if you assume that the whole concept is happening under the spherical symmetry assumption, then this PG and PL on the two sides of this line will be equal, and these two lines are called the impact parameter. This is the most important characteristic of a particular ray path. Every ray is characterized by its own impact parameter. Okay, and therefore we can use this particular height parameter as a function, as an entity of which bending angle is a function. Here I am showing you the earth not in its geoidal form, but we are actually assuming and approximating it by a WGS84 model. This is the model of the earth which best approximates the geoid, and it is being used by the global positioning system as its reference frame. Now what is important now after understanding the occultation plane cross section is that this is a section at a particular time, say t equal to t1. Now if the occultation happens from t equal to t1 to t equal to t1 plus say 60 seconds or 80 seconds, then during this whole span of time the occultation plane will not remain constant. It will actually have an azimuthal shift. Now this azimuthal shift you can actually visualize by this diagram which I am showing at the bottom. What I am showing is on the z axis is the height, the y axis is your longitude, and this is the latitude axis. Now you see at the 60th kilometer in the neutral atmosphere, the signal is now moving downward up to the surface. There is a gradually at every point there is a shift in the latitude and the longitude. So once it has started from this lat long, on the ground it actually shifts by this amount. So this actually is one of the typical characteristics of radio occultation cross ground segment cross section, which shows that actually it is not a point data, but basically there is a drift in the latitude from one point just at the start of the occultation, right at the stop of the occultation, it has reached to some different latitude and longitude. Now this drift of the latitude longitude in the radio occultation technique is basically mission dependent. So if I talk about our Megatropics ROSA mission, there because of low inclination orbit, the maximum drift is only about 1 to 1.5 degree in the latitude longitude. Whereas if I talk about the cosmic, there I have seen that the technique the data is actually drifting by around 3 degrees. So that is the difference, and you can control this drift on the basis of the missions. So now we will come to how the various signal parameters are derived, how we are processing the signals, and let me first start with what happens when the signal is received by the receiver. First, what we do is that we derive what is called the total path delay. Now this total path delay is basically is the measurable. from the time tag which is received by the receiver. Now the total path delay is a known amount, known quantity, and it is mathematically represented in terms of these parameters. One by one, this rho is the vacuum path length between the transmitter and the LEO receiver. Now basically this is the distance that the light travels from transmitter to receiver in vacuum. So this we can actually calculate because we know the speed of light. So, and here, as I said, what is the use of POD antenna? The POD antenna is providing us with the details of the orbital information of GPS as well as the LEO receiver. So we know in the orbit what is the coordinates of XYZ coordinates of GPS and XYZ coordinates of the receiver. We know also the velocity. So we can use the coordinate information and the speed of light to derive this vacuum path length. Now this is the quantity which is happening because of the atmosphere, both the ionosphere as well as the neutral atmosphere. This gamma refers to the delay because of the presence of the atmosphere. The third, fourth terms are the clock error terms, and these terms are actually taken into account because normally these clocks are very precise, but sometimes there are small errors because of clocks, and these have to be taken into account. So we have to take this clock error terms in this equation, and the last term is a thermal noise, which is a random noise, which can be actually considered as a statistical noise, and it can be calibrated. Now what happens is, first step is we try to calibrate the clock, which is called the clock calibration. The clock calibration is used to get the knowledge of the errors in the clocks on the receiver and the transmitter. Once we know this, we know the quantity L and we have calculated rho, so we can actually know this gamma. The gamma is the extra delay due to the neutral atmosphere and the ionosphere. It is the sum of the eta, and the eta is referring to the delay due to the neutral atmosphere, and the total electron concentration divided by square of the frequency, which is actually characterizing the ionospheric delay term. So now we will see how we are deriving from the extra delay due to the total atmosphere and other parameters. But before that, let me now show you the typical excess phase in terms of, say, the time since the start of occultation. You are seeing on the x-axis 0, 20, 40 seconds, and it is increasing. And you see in the beginning of when the occultation just started, the excess phase was very small. It is near 0, but it's not exactly 0, and it's very small. But then gradually with the increase of time, what happens? The excess delay is increasing. What it actually tells us that when the signal was showing excess phase, this excess phase was very close to 0. The signal was actually very at the top of the ionosphere. So you would not expect much delay in the signal. Gradually, as the signal is moving down, it is encountering ionosphere, and therefore you will actually these are the two separate lines. You are seeing the legend for L1 and L2, but because of the scale, these signals are actually coincident, but you will, when you actually shorten the scale, you will see L1 and L2 having slightly different excess phase, because as I have told you, in ionosphere there is dispersion. Okay, now these signals, again excess phase is increasing as we are reaching from top to the lower surface of the earth. So what it is saying, that this is a setting occultation. It means from the top the signal is scanning successively different layers to the lower atmosphere and then up to the penetration depth. Now this is the signal to noise ratio. I have plotted it for L1 signal, and the blue one is for the L2 signal. You see, I talked about scintillation, and in the lower troposphere, just from here lower troposphere starts, and you see large fluctuation in the signal or the amplitude of the signal, and you see this is manifesting in terms of the loss of the signal, because by the time it is coming into the lower troposphere, there is a lot of fluctuations, as you can see, and the signal power has almost reached to the 0 level, and it becomes very difficult here to derive useful information, and therefore we consider that this is from after this point maybe the signal is lost. So we consider the effective occultation time to be the time from which up to which we can actually derive the useful signal. Now we will go to the next slide and try to see how from excess phase or path delay we are actually deriving excess Doppler. Now this excess Doppler is basically, what is Doppler? First of all, Doppler is coming into picture because there is a relative motion between the transmitter and the receiver. The presence of atmosphere adds on to this Doppler, and when we subtract from the total Doppler the effect of the atmosphere, what we get is, no, from the total Doppler, if we subtract the vacuum Doppler, what we get is the contribution of the atmosphere to this Doppler effect, and is called as the excess Doppler. Now this is a typical relations where how we try to derive the excess Doppler. I will actually touch upon certain important points, and here what happens is Doppler is the time rate of change of the phase, excess phase. So excess Doppler, when we have derived the excess phase, we actually try to do a time derivative of the excess phase on both L1 and L2 signals, and these signals are, as you see, these are very noisy signals again. So what we do is we try to find the trend of the signal by actually using what is called the polynomial fitting. Now we are using a second order polynomial fit, and by fitting it, we first of all try to find the trend of the signal and try to discard the noisy part of the signal. Now this is important to do because if you don't do it and directly take the time derivative of the phase, you will be actually incorporating the sub-Fresnel atmospheric structure, and then you will be very it will be difficult to derive other parameters with accuracy. So it is important that you first find the trend. For this we are using the second order polynomial fit, and then you see this kind of trend which we are deriving from these noisy signals. Now once you have derived the excess Doppler, the bending angle can be derived from the excess Doppler by just first of all assuming that our atmosphere is spherically symmetric. By spherically symmetric, I mean that your refractive index of the atmosphere is only a function of the radius from the center of the Earth. So you are actually neglecting the horizontal gradients of the refractive index. Now with this simplicity, what happens is, in this equation, what you are seeing is the total Doppler in the presence of atmosphere, Vt dot Kt minus Vr dot Kr, minus, and you are subtracting the vacuum Doppler, Vt minus Vr, in the absence of atmosphere. So what you are left with is excess Doppler, and as I said, excess Doppler is the time derivative of this excess phase, which we have already derived earlier. Now in terms of components, what happens is, when you break it in terms of components, you make use of this particular diagram or the geometry. Here I will first of all tell you about the terms. The transmitter is on this side. This is showing that GNSS velocity, and this is the direction in which the signal was propagating. Then after bending, it is being received at the receiver in this direction. So KT refers to the direction of propagation of the transmitted signal at the time it is transmitted, and Kr just refers to the direction of the reception of the signal at the time it is received at the LEO receiver. Now, as I have actually discussed, this angle between this particular thing is the bending angle. Now from the triangle law, if you know, this angle of the triangle is the sum of the internal angles of the triangle, delta t plus delta r. Okay. So it means if you want to calculate bending angle, what you need to know is the sum of this delta t and delta r. How do we extract this? So for this, what we do is we break this whole vector equation in terms of components by making use of these angles. So first equation is the excess Doppler, and this equation now broken in this component form. So we require another equation because we have two unknowns, delta t and delta r. So another equations which we get from the Snell's law, and it's actually what is happening is we are using the Booger law, which is the equivalent of Snell's law for the spherically symmetric medium. So it is represented by A is your impact parameter, which I have already discussed. Impact parameter is RT NT sine theta t plus delta t and RR NR sine theta r plus delta r. These angles you can actually relate from this diagram. So we solve these two equations iteratively by first assuming that delta t and delta r are both 0, and then we solve it and then iteratively change the values of delta t and delta r till we get a convergence. So the final value of delta t and delta r at the convergence, when we add them, we get the bending angle. Now at the outset here I will make it clear that although I am showing one alpha, basically because we have two signals L1 and L2, we are basically solving this equation for both the signals. So we will be getting one alpha 1 for L1 signal and another alpha for the L2 signals. So we will have two bending angles. Now these two bending angles are happening because as we have already seen, the ionosphere disperses the signal and they are actually coming from two different paths. So the bending angle will be slightly different on the two different signals. We have to make sure that when we actually do the solution for neutral atmosphere, we remove this ionospheric contribution. And here I will say how we are doing this ionospheric calibration. Now you see, this is a very simple relation. The alpha 1 on signal L1 and alpha 2 at signal L2 as calculated from the earlier slide. Now it is actually weighted by this combination of the frequencies, where F1 and F2 are only referring to the frequency of L1 signal and F2 to the frequency of the L2 signal. And when you take this linear combination, you actually remove the noise of the ionosphere, and what you get is the alpha. Now this is a first order correction of the ionosphere. Now what is important is that with this correction, you don't remove the residual ionospheric part in the data. Now this still remains there. So what is required is some statistical optimization technique. This work has been done, and I've been on the statistical optimization technique on megatropic ROSA data. And here I am showing one result. What happens here is, you see, this is the relative difference when we did not apply the statistical optimization technique. Here, the relative difference at 35 km was around 15 to 20% in the bending angle. Now, after application of the statistical optimization, we are showing for three different weights which we considered. The first weight was shown by this black line. Still, it is at around 10%. But when we further refine the weights, what happened is now you see a very smooth, and the difference has reduced by a very large amount. Now we are only left with around 3% at 35 km. So we are effectively, with statistical optimization technique, we have reduced the ionospheric contribution in the neutral atmosphere bending angle. So these two steps are important, which we call as ionospheric calibration. Now once we have calibrated the bending angle, we are left with what is called the neutral bending angle, and this relation actually helps us to derive the refractive index as a function of the radius from the height from the center of the earth to the tangent point, and this integral is called the Abel integral transform. Here alpha is representing your bending angle. When you solve this integral, you actually try to invert the bending angle to the refractive index. Now refractive index, as you know, in the atmosphere, refractive index is a very small number. Like vacuum, refractive index is just 1. So what happens is, when you actually don't work with such small numbers, so we try to scale it by multiplying it with 10 to the power 6. So on the LHS, the term is called refractivity. So this is what we consider in radio occultation mostly, and we will see how this refractivity is now related to atmospheric parameters. So this is a relation given by Smith and Weintraub in 1954. It's an empirical relations, and what it means is that basically these K1, K2 and K3 constants and K4 have been empirically obtained, say, by a very large study, and these values are now actually fixed, and they normally actually have been accepted worldwide, and people are using these relations for modeling the refractivity of the atmosphere at microwave frequencies. Now, the first term is the dry pressure by temperature. Second term is the water vapor. E stands for water vapor divided by temperature. E is again, there is a third term E, but here we have temperature to the power 2. And the fourth term is the contribution to the refractivity from the ionosphere. Here we will not consider the ionospheric refractivity term, as we will be deriving only MET parameters. Now with this parameter equations, now this is a typical illustration. You see the first term, which contains the dry term, the dry pressure and the temperature, is basically shown by this. So when we extract this term, this is called the dry refractivity, and the rest of the two terms refer to the wet refractivity. Here wet because we are incorporating the water vapor or the humidity information in the refractivity. So we will see our simulations. Let us see, because now you know this equation. So what happens? You can actually, if you have a temperature, pressure and the water vapor information, you can actually simulate and try to see for yourself what is the result of refractivity in the different latitude that you are getting, and you can compare it with, say, radio sonde or other data models. So here is a typical simulations which I did. Suppose I am taking a different temperature, and we are actually using this pressure information, then the specific humidity, or maybe the water vapor pressure information we can use. With these three terms, we have modeled the refractivity. The continuous line is for the dry refractivity, and you see the wet refractivity just at about 10 kilometer and below stands separately from the dry refractivity, which means the contribution of water vapor actually is affecting below 10 kilometer, and that makes the wet refractivity, which is the total refractivity, to be larger than the dry refractivity. So this is a simple simulation thing which you can also try. Now again, I have shown how bending angle can also be derived from refractivity. So this I will not dwell upon, because you have already come across the Abel transform and you can see for yourself how it is done. So now let us come to the parameter retrieval technique, which we have actually used for deriving it from the Megatropic mission, ROSA mission. Our technique is based on what is called a two-tier approach. It's a two-step process in which we are demarcating the height of the atmosphere, which is known as the water vapor point. Now we know this equation from the previous slide. What we have done is we have combined the E by T term to the PD by T term, and what P is referring is the total atmospheric pressure now, because total pressure is dry pressure plus the humidity. So PD plus E, and you combine this term, you get one single term. So now if you suppose assume that E is 0 at a particular height, say above the water vapor point, we have seen that the dry atmosphere can be assumed. So E is 0, then you are left with this particular term from the equation 1. Now you have two unknowns, pressure and the temperature. So you require another equation. This equation comes from the hydrostatic relation. dP by dH is minus G rho. Now here your rho is the density. The density is again a sum of dry density and the density because of the water vapor. So you can actually use this relation to get the density information. You put this relation here and use the knowledge of n from this relation. When what you get is the total, this kind of relation, which is called the equation, which we call as equation 2. Now from equation 1 and equation 2, in equation 2 also we assume E to be 0. So we are considering dP by dH is equal to minus G by K1 md R by R into N, and the first equation term K1 P by T. We have to solve these two equations simultaneously for P and T. This will give us what is called the dry pressure and the dry temperature terms. We will see a particular profile of dry temperature in the next slide. Just to make you clear, see, this is the typical temperature profile, and I am showing you up to the 20 kilometers. Now you see that at this point, which we are calling as water vapor point, this is somewhere around 10 kilometers. The dry temperature is this one, and actual temperature of the atmosphere is this. So definitely the dry temperature which you retrieve is good above 10 kilometer, but below 10 kilometer, that is below water vapor point, you need to make corrections so that you get the actual temperature profile. So this particular retrieval in the below the water vapor point is called as wet retrieval in our processing algorithm, and we will see it in later slides. Now similarly, you see in dry we are seeing the cold bias in the temperature, which means the temperature which you have retrieved will always be lower than the actual temperature of the atmosphere. If you can actually conclude from here, your dry pressure will actually be higher than, it will have a warm bias. So it will be higher than your actual pressure in the atmosphere. Now we have done some validation study for our dry retrieval algorithm, and this figure on the left is showing the continuous line, which is the mean bias, and the standard deviation of the temperature profile. You see, we are showing only above water vapor point the validation for the dry parameter. And what we have done is we have actually retrieved the dry parameter from the algorithm and then compared it with the actual temperature. So at 10 kilometer, our accuracy is better than 1K. And as we move above 12 kilometer, it further gets better and it is less than even 0.3K, and it remains that up to about 25 kilometer, and then slightly exceeds at about 30 kilometer to about 0.5K. In terms of pressure, the accuracy which we have achieved with this algorithm is 0.3 millibar at 10 kilometer, and above 10 kilometer, it further gets better in terms of standard deviation. So this algorithm has been actually validated for the dry parameters, and we can consider this dry parameters to be our true parameter with these kind of accuracies in our applications. Now we will see how to actually correct for the temperature and the pressure and derive humidity information below the water vapor point. This part of our retrieval algorithm is called the wet retrieval. Now this is based on a typical suggestions which was taken from O'Sullivan et al. 2000 paper, and suggested that temperature can be assumed in the tropics to be quadratic in the natural logarithm of pressure in the water vapor dominant region. So this can be mathematically represented by this equation, where T is the temperature, sigma is the natural logarithm of pressure. So we are denoting it as A plus B sigma plus C sigma square. And to validate it, what we did is we actually did 2 experiments and took the actual temperature data from radio sonde, which we are showing on the left side, and from the NCEP model on the right side. And we actually used the quadratic fit relation, which we have plotted on the y-axis. And then you see this scatter plot has been actually shown with the R value of 0.96 in the radio sonde and 0.99 in the NCEP. So this actually validates the consideration of this particular assumption. So we will progress with this particular relation for our wet retrieval. Here our objective is to find out A, B and C, the coefficients. So what we are doing is, first is we have 3 unknowns. We actually solve it by considering the temperature and the dry pressure to be true at the water vapor point. So what we get is one relation from that assumption at the water vapor point. Second, we are assuming for the surface values, the temperature and pressure at the surface. This actually we have prepared a data set from the existing models, and we have considered the climatology of the surface pressure and temperature, and this data we are regularly using, and this helps us in knowing the surface values of sigma and the temperature. So with these 2 assumptions and the third equation which is given by this relation, we are actually solving for A, B and C coefficients. Once we know the coefficients, in the first cut, what we are doing is we are assuming the dry pressure which we have retrieved below the water vapor point as a sigma. We are taking a natural logarithm of that dry pressure as sigma and putting in this relation to get the first cut temperature. Then after we get the first cut temperature, we put the first cut temperature, the known refractivity and the dry pressure in this relation to get the water vapor information. This water vapor information is then ingested to get the water vapor mixing ratio using this relation, and from that we derive the virtual temperature and solve again the hydrostatic equation, where when we solve it in the second iteration we actually get the refined pressure. This refined pressure we calculate the refined sigma and then again re-estimate the temperature. So this process is an iterative process, and it continues up to 3 to 4 iterations by which it actually converges. The value of temperature, pressure and the water vapor pressure E at convergence is the final retrieved value of the parameters. Now I will show one example which when we actually applied this wet retrieval, and you see actually we have shown up to 60 kilometers. This part is the dry, and you see the dry has been, the black one is our method and the red one is the cosmic data. You see the comparison. The dry one is actually comparing very well with the cosmic one, and you see the wet retrieval starts somewhere here, and again it is following very good match with the cosmic. Here we are showing it for the water vapor. So now we did one validation for with the simulation data in order to understand the accuracy of our algorithm. And here I am showing a zonal distribution of our accuracies in temperature and the water vapor pressure. So you see, normally, as I have said, the ROSA data is only covering only up to say -30 to 35. So we have restricted our NCEP simulation only up to 30 to 35 for the sake of the ROSA data only. And this is the standard deviation. The left side is showing the mean bias of temperature. Below again, it is the mean bias of the water vapor pressure, and this is the standard deviation of the water vapor pressure. So you see, mostly our temperature accuracy is up to around 8, is around less than 1 K in temperature. And then at some levels inside, say below 7 kilometers, particularly in the tropics, as we have seen that in tropics there are a lot of changes in the moistures, and there what happens is sometimes the accuracy of the algorithm may degrade, but it is going up to 1.5 K. And then you see certain patches at around -30 and 30 K, where sometimes you see the higher values of the temperature. Here the accuracies are sometimes reaching up to 3 to 3.5 K. Now these particular cases have been analyzed with respect to say even the refractivity data. Now if the refractivity has certain inaccuracies, then this may actually result in this kind of error in the temperature. And sometimes it is also because sometimes the sampling is not much over here, so you don't get much collocated data. In that sense also your comparison may be a little degraded. Now in water vapor also we are able to achieve accuracy largely up to around 0.4 millibar, up to around 3 K, and then there are certain higher values which can go up to 0.6 to 0.7 millibars. So this is the current accuracies with the algorithm. And this is a new technique on the one-dimensional variational technique. I will not discuss in much detail over here, but this is an important technique to understand. So what will happen is, here we are considering that, see, you have an observation data set in terms of refractivity, and what happens is you actually try to compare it with respect to a background data set. The background data set is taken from any known data set, which is the a priori data set. It can be from the model, it can be from the radio sonde, it can be from the regression also. Now once you tune that background data, what you are doing is you are actually comparing your observation data with the background data by weighting it with their respective error covariances. Now these error covariances play an important part, and I will just show in the next slide that the relationship is given by this particular relation, which is the cost function, and it is written as half x stands for your state vector which is to be retrieved, xb stands for the background data, b is its respective error covariance matrix, and y is the observation data. Here we will fill y with our say radio occultation refractivity. H of x is our refractivity model, where what is happening, we are actually using the background data of temperature, pressure and the humidity information and deriving the simulated refractivity. R is the error in the observation. Now these are important components which helps us in finding the cost function. So you can see in matrix notation, this will be written in this kind of vectorial form. So your y0 will consist of refractivity at different levels, Z1, Z2 up to Zt. And then you will actually use the temperature from the background data, then the humidity and the surface pressure, which you can use as the background data. And here the background data is first of all used, and then it is interpolated to the location of the of the refractivity, and then from there what we are doing is we are deriving the forward modeled refractivity observation. This is the typical error covariance matrices. We are showing it for the refractivity, and this is the error covariance matrix of the background data. So with these information, what you have to do is we have to actually minimize the cost function. The cost function minimization means what we are taking is the gradient of J, and it is given by this mathematical relation. Now you see this particular illustration in a 3D geometry. Now suppose the starting point with the background data was J, the minimum point of J is here. So by actually using some very non-linear, this is a non-linear problem. So by using non-linear minimization technique, one can use the Levenberg-Markov method, or one can go for the Newton-Gauss or quasi-Newton method also. One sees that gradually, one by one, you are changing the gradient and then trying to nudge it to the minimization point of the cost function. At the minimization point, whatever is the value of X that you have achieved is your retrieved optimized solution. So this is a very state-of-the-art retrieval technique, and actually we are also into this refinement, and we are very shortly going to come up with this kind of technique also. Now let me make you understand about certain application areas of GPS RO data. Here, three broad categories where this data is finding a wider use. First is that because of its long-term stability, which I said, it is having climate quality data set. Now, very accurately, it has been called as the world's most accurate thermometer, because the temperature accuracies which we are getting is not found even from other satellite soundings. In meteorology, actually it is an all-weather capabilities technique. So basically it is being used directly by the various numerical models to find for the global weather forecast and analysis. People are also used this data for the tropical hurricane or the cyclone systems, convective system studies. And I will show one particular result for the Ernesto storm. It was studied in the very long back, and people have actually used that kind of analysis for giving importance to this kind of technique. In the ionosphere, people have been using it for deriving electron density distribution. One can derive the tomography, which is the two-dimensional and the three-dimensional distribution of the electron concentration in the ionosphere. And by seeing their variability, one can also monitor the space weather. So these are the broad areas where actually GPS data have been regularly finding its application. Now I'm showing you this particular Ernesto storm situation. You see, this is on the left hand side. I'm showing the diagram which was obtained from IR sounding, and this data very clearly shows one actually hurricane developing over in this region. And then what happened? Very fortunately, one data from the radio occultation was available at the same latitude. So an experiment was done where first of all this data was not assimilated in the model. So you see the right hand side figure, the extreme right, you don't see that kind of features when the GPS RO data was not assimilated. Now as soon as it was assimilated, you start to see this kind of features which is matching in terms of both structures, the spread, as well as in terms of location also with your adjoining IR diagram. So this makes a clear case for this technique to be considered in future for such kind of studies. Then one can also derive what is called integrated water vapor, and you see different color codes of these dots shows that where your the integrated water vapor is more, where it is large. So all these informations you can actually derive from the radio occultation. Then one can also use it for planetary boundary layer studies. Here one typical study which has been done at NCAR Boulder. Here they have been showing what is called the atmospheric boundary layer depth. So no other satellite and not even models are today capable of telling you very accurately the atmospheric boundary layer depth. And for boundary layer physics and studies, this height determination is a very important research area which is being used and actually being retrieved using this data. And one study which actually I conducted in the United Nations STEEPS SATMET project I am showing here is the identification of double tropopause. So normally, because of its very high vertical resolution data, what is happening is, let us see, you are very able to actually distinguish between the first tropopause and the double tropopause. Now, there are three different methods which we actually used. One is showing the cold point method. Normally, the cold point method is wherever you have a temperature minimum in the atmosphere starting from the surface, you consider it to be the tropopause, and that height is your tropopause height. So in the tropics, this method works well. But when you see on the right hand side, I'm showing for the, say, 78 degrees. So this is the mid latitude polar region, and another in the extra tropical region. Here you see, normally you are with the CPT method, what you are getting is a higher value of the tropopause, which is anomalous. So what we do is we basically use the WMO method for the polar and the mid latitude regions. So here in the project, we actually used another refractivity method, and we actually found that the WMO method and the refractivity method were actually giving one and the same result in terms of the tropopause height determination. Now the green ones and the purple one which you are seeing are the first tropopause and the second tropopause. The purple one on the below is your first tropopause, and immediately above we are getting the second tropopause, and both the method is giving the same height. So this is one important study with the radio occultation data, which you can also do. Now, once you also determine tropopause, you can go for the morphology of tropopause. This was also done under this project. And what you can do is this kind of spatial distribution of the tropopause height or temperature, pressure can be actually created. And I have validated with, say, I'm comparing qualitatively with respect to the NCEP data. Below, you see on the first row, what you are seeing is the tropopause pressure from our method, and then we are comparing it with the NCEP data. You are seeing a very good match. And then you are also, I'm showing the temperature at the tropopause, its spatial distribution, and then comparing with the NCEP. Here again, we found a very good match between the two. So basically, with this radio occultation data, you can go for such kind of long-term tropopause morphological studies and understanding the variability. So now with all these things, let us see where does this technique stand in terms of other remote sensing instruments. So we will actually, I have put this particular study which has been brought out by the committee on, there's a global committee on observation, a global climate observing system. And this committee actually recommended, after seeing the impact study of GPS-RO, that basically GPS-RO in terms of this is the impact per dollar of the observation. See how much you are actually deriving the benefit and how much is the cost going for the instrument. If you do that kind of analysis, you will find that the GPS-RO is having the maximum impact in terms of all other satellites and the sensors. So this is one important thrust which has given a lot of incentives for this technique to be taken ahead in future. And this is the scenario, what were the missions in the past and then present missions and what is going to come in the future. So at present, we are actually having this cosmic mission is going on, and this is the research mission. Our own ISRO's missions were on OceanSat-2. This is still going on, and we have the Megatropics ROSA mission. But these are basically research missions where we are actually trying to do it for the kind of validation of the algorithms and those things. In the next phase, when the maturity has been achieved, we will be actually going for the operational missions. And in the world, basically, there are few operational missions right now. We are having the METOP A, METOP B, and C will be coming at around 2017. And these are the European missions, and very soon this cosmic mission is going to be launched by the NASA. So you see the scenario for the radio occultation missions till up to 2027 is very bright, when we will have a lot of data from these missions. And then you see, seeing the benefits, some commercial agencies are also launching these kind of sensors. Like Cicero missions is actually a commercial mission, but actually they are charging for the data. So that is the only some kind of hurdles, but otherwise these data are also available from commercial missions. Now, Just a small statistical thing in terms of how these data are being received in different grids of the Earth. So you see, what I actually shown till now is we are considering one low Earth orbit receiver, and suppose you consider only GPS transmitter, and there we have seen that we were getting some amount of data. Now when you consider 6 LEO and you consider GPS as a transmitter, you are getting approximately about 3112 soundings. Okay, this is the per day. And when you divide these soundings as received on the Earth's surface in terms of 400 by 4 kilometer, you consider an area and divide it in terms of grids, then in each of these grids you are maximum at least getting up to 1 to 1. So one effectively, if you consider integral, one data per grid, so in a day. So this is a very small number, and naturally people like weather forecasters would like to have more data available in the grids. So what is the solution? Actually the solution is whether you can actually increase the number of LEO receivers in the orbit, and you see as we go on increasing, and we also try to increase the number of transmitters. Now we are adding the GPS, then GLONASS, then you add on Galileo. With these kind of studies, one has come out with these final numbers. Suppose we consider 48 LEOs and all these transmitters, you are getting around 36 ROs per grid, this 500 by 500 kilometer grid, which is a very adequate number. So you see, this is how we are trying to go in the future and trying to solve some of the data density problems. And this is the typical depiction of the same statistics in terms of the grids. You are seeing with 6 RO constellation, as we are increasing the number of their transmitters, you see the density is increasing per grid. And similarly, when the 12 RO constellation, it is increasing. This is a study actually has been taken from the NCAR Boulder, and they have done this study, and accordingly they are coming up with this Cosmic 2 mission, where what they are trying to put is, instead of 6, they are putting 12 RO constellation, low Earth orbit receiver. Therefore, you are seeing the kind of density of the data which you will be getting per day. Actually, their estimate is around 12,000 profiles per day. And right now with Cosmic, you are getting around 2,000 profiles. So there is a big jump. So this data will be available by around 2016 or 17, probably if they launch it in time. And thank you for your attention.